Thank you all for joining this talk, and thanks to the organizers for setting up this online conference. Contributing on ZIO was an opportunity to know such friendly and awesome people like Adam, and I'm happy to co-present with you. Adam.
Yeah, thank you so much. It's great to be here with you, and thank you so much to everyone who's taking the time to be with us today. So today we're going to talk about fiber supervision in ZIO. So we're going to start by talking about what fibers are, and then from there we're going to talk about what is fiber supervision and how does it help us write safer concurrent code.
Yeah, and fibers are built on ZIO, and ZIO is a Scala library for concurrent and parallel programming. It provides data types called ZIO of REA, which enable us to write purely functional code, because this data type will model effects, will describe our programs, which would be a bunch of interactions with the outside world. And so we can combine our programs, and we can build a program from another program using this data type. And for simplicity, we can see this data type as a function that requires an R and either fail with a value of type E or succeed with a value of type A. In case if your program doesn't require any environment or will never fail or fail with throwable, and you think that ZIO has many data type, type parameters, you can use the type aliases of ZIO. And when you are writing your program using this data type, you are going to describe everything. And when you execute the program, nothing will happen, because everything will be a description of your interactions with the outside world. So how could we run an effect in ZIO? The first step is to provide the environment to feed this function in order to get out the result. But your program you might have concurrent programs, and either will not describe that you are running something. And in ZIO, there is a data type called fiber, which models a running IO. And whenever you build a concurrent program, it will be described as a fiber. And if you execute a program, a simple program, I mean a ZIO program, it will be internally also executed in a fiber. And how to run your effect, you can extend the ZIO app, or you can call unsafe run in your effect. And then this will interact with the runtime, the ZIO runtime. So now let's understand deeply what is a fiber. Adam, what is a fiber? Tell us.
Yeah, thanks, Wiem. So you can think about a fiber as a lightweight equivalent of an operating system thread. So just like a thread, a fiber describes a running computation that's potentially happening at the same time as other computations. But there are some key differences between fibers and threads that are really important. So the first one is that fibers are much more lightweight than threads. So in an application, you could have tens or hundreds of thousands of fibers at a given time, whereas if we ever had that many number of threads, we'd be dramatically reducing the performance of our application, because we'd spend so much time switching back and forth between them and managing them. Second key difference is that fibers can semantically block, but they never actually block any underlying operating system threads. And the third difference is that fibers are safely interruptible. So we're going to go into more detail on each of those in this talk. On this page here, you can see the signature of a fiber in ZIO. So a fiber is parameterized on an E type and an A type. So a fiber is a computation that will either succeed eventually with a value of type A, fail with an error of type E, or go on forever if it's not interrupted. And fiber, what's more, is an in-flight computation. So versus everything else, when we see a ZIO, that's a description of a program. A fiber, if we see it, it's not suspended another effect instructor, that's a running computation that's actually happening right now. So there are a couple of fundamental operations on fibers, and the first one is forking. So forking creates a new fiber, a new running computation, and the way we do that is with this fork operator on ZIO. So this takes a ZIO that's describing some computation, and it gives us back a new computation that is now, instead returning an A, it's going to return this fiber VA. So it's describing this fiber that's running that then we can do other things while this fiber is running or work with this fiber, still all describing this as we build up the rest of our program. So how does this actually get implemented?
For example, if you have an IO, when you create a fiber using fork, this fiber will execute the instruction inside this IO. For this example, it will go into print out in the console hello world from a fiber. Let's see how this happens internally. Each concurrent task will be stored in a queue, and each fiber will take tasks and execute them. They execute a specified number of instructions in case if there is a task, for example, task 2 takes a lot of time, has many instructions, and the fiber, it's more than the specified number of these instructions in the fiber. This task will be suspended and the fiber will put it back in the queue, and it will take another task, and this, like, the instructions will interleave each other's. One of the other fibers can back and run that task again. And then in the ZIO runtime will take this fiber from the queue and execute them using the underlying operating system thread.
So the result of all this is that we can have many more fibers than the number of actual threads that our program is using. So our program might only be using, say, 4 threads if we have 4 cores on our computer, or maybe only 1 thread if we're writing our program on Scala.js. But we can have concurrency with, say, 10,000 fibers at a time by each fiber just getting a little bit of execution from one of those operating system threads and us switching back and forth between them. So it lets you as the user work with this very high level of concurrency while the ZIO runtime manages the actual underlying threads for you. So I think the other thing to remember when we talk about forking fibers is that every effect in either ZIO or other functional effect systems in Scala is ultimately running on some fiber. So if we're using fork, we're explicitly creating new child fibers that are going to do part of the work. But even if we never call fork, when we go to run our program at the end of the day, that whole program is going to be running on some fiber. So think about whenever you're running a program, there's always some fiber that's actually doing that work for you. So we talked about forking fibers, which is the first fundamental operation on fibers. The second fundamental operation is joining fibers. And whereas forking is creating a new fiber, joining is ending a fiber's life and bring the result of that computation back into the main logic flow of our program. And this is done through this operator join that we can call on any fiber, and it's going to semantically block until the result of that fiber is available, and then it's going to return us a new computation that has that result. and it's going to semantically block, but it's never going to block any underlying operating system threads.
For example, if we have a fiber, for example, fiber 1 has a child fiber, which is created here in, it forks computation, and later fiber 1 want to join this computation. It actually will wait for the other fiber to complete and to take the result, and it will enter a suspended state, so it will not move to the next instruction, and it will register a call back to the fiber 2, and once the fiber 2 will complete the computation, it will ping the fiber 1 that the result, and then the fiber 1 will continue executing the next instructions.
So the result of this is that as programmers, we get to write our code in a very intuitive, straightforward way where we say, do this, do that, do this other thing, wait until this is completed. But under the hood, this is completely non-blocking because there are all these callbacks that are being invoked, but we don't need to be the ones who manage all those callbacks and have to deal with those and make sure those are piped the right way. The ZIO runtime does all of that for us.
Is that like future.await?
Yeah, so that's a great question. So it's actually not, because future.await blocks the underlying thread. So if you read the documentation for that, it basically says, do not use this if at all possible, or do it at the very end of your program, versus joining a fiber is completely non-blocking. So it's perfectly safe to do that whenever you want to in your program.
Nice, makes sense.
So we talked about forking to create fibers. We talked about joining. The other way that we can end the life of a fiber is through interrupting it. And this is really important, the real differentiator versus threads or even working with futures, because those aren't safely interruptible. Futures not interruptible at all. Threads you could interrupt, but we can't do it in a safe way. Versus fibers can be interrupted at any point. And that's really good for conserving resources for us, because we might have a situation where maybe we're serving a request from some website, the user clicks on a button and we want to kick off a bunch of work, but once we get started, they close the web page. So now there's no point in us doing all that. We want to conserve resources. We want to say, stop that computation immediately. And so fibers have this method interrupt on them that essentially says, don't execute any more instructions in this computation. We don't need the result of this anymore. And going back to that point about safety, the thing that really allows us to do this is we also have the ability to attach finalizers to these computations. So if we just had a thread and we said, oh, we're going to interrupt the thread, we might be in a state where maybe we've opened a file, but we haven't closed the file, or do something else that leaves us in an inconsistent state. So we can't really do that in a safe way. Versus with ZIO, we can attach finalizers with operators like ensuring, that here, when we call ensuring on a computation, we say this finalizer has to be run when this computation is done, no matter how the computation finishes, whether it's successful, whether it's failed, whether it's interrupted. And that, along with another one called bracket that's similar to it, are really the building blocks for us being able to use resources safely within fibers and within concurrent code that could get interrupted.
How this happens, it's, for example, if we have two fibers are executing tasks, if they will run them while they are not interrupted. And if, for example, task 3 decides to interrupt task 1, the fiber will stop executing the task 1 instructions and directly will run the finalizer, and then it will remove this task from the active fiber and take another task, and the same mechanism will be done.
So we talked about interruption. The other key building block for us to have is sometimes we need to be able to turn interruptibility off or on. So we already encountered that once before, and we talked about finalizers. And part of the point of finalizers is we wanted to say, even if this effect gets interrupted, we still need to make sure we close that file handle, or we still need to make sure that we shut down that connection. And part of that is we need to make sure that that finalizer doesn't get interrupted itself. So we have the ability with these operators like interruptible, uninterruptible, as well as some other variants of them, to control in a very fine-grained way when our effect can be interrupted and when it can't, so that we can say, look, I'm starting some important computation where I need, if I start this, I need to be able to finish this, and we can express that in our code.
And each fiber has internally its state, which indicates whether it is interruptible or not. And then we can also have control over our effects, and we decide if they are interruptible or not using these operations. And for example, in case if a fiber, a task is interrupted, the fiber will stop it only if it is interruptible. So we understand what is fiber and how they work. What about the fiber supervision?
Yeah, so far we've really been talking about one fiber, how to create one fiber, how to interrupt or join one fiber, what operations we have on one fiber. And we've been talking about things that are pretty similar across different effect systems. So if you looked at Monix, you looked at CATS, all of that would be pretty similar. Fiber supervision is about what happens when we have more than one fiber. So let's say we have a parent fiber that forks off a child fiber to do part of its work. What happens there? And that's where we start to see differences between some of these effect systems.
Yeah, for example, we have a fiber parent, John, and he wants to give work for VM, and VM decides to ask Adam to help her. And the topics are she took the high priority topics, and Adam starts researching for the other topics. What would happen if, for example, if VM finished the research and John decided to take that result, and which is successful result, what happens for Adam's research? He might still researching on the topics. And in case of failure, what if VM failed to search the topics? What will happen for the work of Adam? And in case if John decides to stop the work and interrupt the fiber, VM's fiber, what will happen with the work of Adam? This, like.
So let's start to see what this looks like in code here. So on this page, we've got an example. This one is working with ZIO. So this is not using the same type of fiber supervision framework that ZIO uses. And so here we've got a parent fiber that is going to sleep for 3 seconds and then is going to print hello from a parent fiber. And it's going to, before any of that, it's going to start a child fiber that's going to sleep for 5 seconds and then say hello from a child fiber. And then in our main program, we're going to kick off that parent fiber. We're going to wait a second for it to be able to start and for it to be able to fork the child. And then we're going to cancel it. So this is the equivalent of interruption in ZIO. And then we're going to wait and see what happens. And if we run this program, we'll see that the parent gets interrupted because we canceled it. but the child fiber is actually still running because it was forked off before it got interrupted, and we don't have fiber supervision here. And so the result of that is that this fiber, after these 5 seconds, is going to print hello from a child fiber to the console, even though we tried to cancel the entire computation here.
Oh, this sounds quite dangerous. What if the child is using the resource of the parent? What would happen?
Yeah, so that's the issue here, that in this case, we were just printing a line to the console, so it doesn't really matter, it's just an example here. But in reality, this child fiber could be acquiring resources, it could be doing compute and racking up cost on some cloud service. We don't know what this fiber is doing. And there are other combinators that we could use with this effect system to make sure that interruption did happen. But it's a little bit of a gotcha for us, where if we just write code in the ordinary way, we end up with this potential risk of a resource leak. And it also interferes with our ability to reason locally about our program. Because what we'd like to be able to say is that forking fibers is, to a certain extent, an implementation detail. That if I need to calculate pi to 100 digits, if I do it in one fiber and I just do all the work, or I fork off 4 different fibers to do parts of it and then I put them back together, that those two things should be the same. That's just a optimization, a safe refactoring that I can do. But what we saw in that example on the previous page is that if we don't have fiber supervision, that's actually not the case. That by refactoring my program to have this child fiber printed out instead of just printing it out myself, I actually changed the meaning of my program and how it responds to interruption. And so a way to zero in a little bit more on what's actually wrong here is this concept of fork join identity. And so the idea here is that if we need to do some work, if we fork that off to a child fiber, and then we bring that back into our main computation, that should be the same as if we just did it ourselves. And that's kind of a way of formalizing that notion we're just talking about, that whether we fork something or do it ourselves should be an implementation detail that we control, but that doesn't change the meaning of the rest of our program. But what we just saw is that one of the necessary conditions for that, it's not a sufficient condition, but a necessary condition for that, is that we have a part of our fiber supervision where we say, if the parent fiber, if the supervising fiber gets interrupted, then it needs to interrupt its children. And similarly, if it fails, it needs to interrupt its children and prevent them from continuing. So here's the same example in ZIO. And the code is very similar. It's basically the same, except we put a Z in front of everything, because that's what we like to do in the ZIO world. But the behavior is going to be different here, because when we run this program in ZIO, we're going to interrupt that parent fiber. And then as soon as it's interrupted, it's going to turn around and it's going to interrupt its child fiber. And so as a result, this hello from a child fiber line is never going to get printed. And so this idea of supervision lets us recover some of that local reasoning that we lost before. And because supervision is hierarchical, where if I'm supervising a fiber and I interrupt them, and then they're supervising the other fiber, then on the interruption, they'll interrupt that child, I get this property that if I fork off some computation, that computation may fork off 1,000 different fibers, 10 layers deep. But if I interrupt that, all of those are going to get interrupted in a very logical, ordered fashion. So it lets us recover some of that ability to reason locally about our program, as well as that resource safety.
Well, sometimes it's unfair if you would start doing work by yourself and then the parent fiber interrupts me, and it would be unfair if you stop working. Is there any other choice to, I don't know.
Yeah, so fiber supervision is a really good default. Most of the time, if we fork off some fiber to do some work and we get interrupted or something happens, we want to interrupt that child fiber. But that's not always the case. Sometimes we just want to create some kind of background process that's maybe going to outlive us. We want to send a heartbeat signal somewhere, or we want to do something else. And for that, we've got a concept in ZIO, we call it disowning a fiber, of essentially you say, I was responsible for supervising this fiber, but now I'm going to disown it. I'm going to say, now this is a completely independent fiber. It's its own root fiber that is not supervised by anyone else. And if I get interrupted or anything else happens to me, that fiber is going to continue going. So you can do that to any existing fiber with this disown operator. For the common case where you just want to essentially disown it as soon as you create that fiber, you just want to say from the beginning, this fiber is an independent fiber, we have this fork daemon operator. So you could think about it as like a daemon thread that's going to continue independently for the life of your application. So this is great. Sometimes you need this. We think that the supervised model is a better default, but you've got this if you need it. Just my advice would be try to use this sparingly, because that supervision model is really there to help you and there to make sure that most things only make sense for some scope. You don't just want them to continue indefinitely forever. So be judicious about when you use this.
Yeah, I think we should be wise when we use it, but like we should be, is there something like the perfect scenario would be, for example, if I would be interrupted and John will be your supervisor, at least, I don't know. Is there something like this?
Yeah, so you're getting in a way to the open issue that we've been working on recently in ZIO. And so far, we've really focused on this situation where the parent fiber is interrupted or fails. And there, it's pretty clear that the parent fiber should be interrupting its child fibers. But a little bit of the harder question is what happens if the parent fiber just ends life normally? So you fork some process, that process is still going, the parent ends, what happens? And ideally, in a way, we'd like to do what you just said, and also what's intuitive if you think about just like being an employee at a company, of if I'm going along and my boss takes a vacation, well, then I've got to essentially report to my boss's boss. They've got to step in and supervise me and make sure that I'm doing the right thing and tell me to stop doing something when I'm supposed to stop doing it. But that ends up being challenging to implement with fibers, because each one of these fibers is a running computation that state may be changing all the time. So we may have a situation where I'm working for you and you go on vacation. So we want to say, okay, I'm supposed to now report to your boss, but maybe your boss has gone on vacation, or maybe your boss has changed, or who knows what's happened. So it creates this challenging situation where we need to synchronize on multiple fibers to find one that's actually an eligible supervisor for me. So we've dealt with this a couple of different ways in the last couple of release candidates as we've introduced this fiber supervision model. So in release candidate 17, we actually try to do this, what we call transplantation. So when the child fiber's parent terminates, we try to move the child up to the grandparent. In a way, that's what's ideal for preserving this fork join identity, but it led to concurrency issues with being able to do that in a safe way where we didn't have any types of race conditions or other concurrency issues there. And it also sometimes could lead to fibers lasting longer than actually made sense, because if we had a fiber that was forked at a lower level of the application, and its parent ended, we just keep moving that fiber higher and higher in the application. But there's a point at which typically it doesn't make sense to keep doing that. If you think about being at a company, if I'm working for you and you go on vacation, okay, it makes sense for me to report to your boss. But if the entire engineering department gets shut down, then I should probably just stop doing what I'm doing. So then in release candidate 18, we took a little bit of a different approach of, we said that fibers, when they were finished, they would automatically interrupt all of their child fibers. So this was very good for resource safety and addressed that concern I just mentioned, but it actually violates that fork join identity because it can lead to effects being terminated too early relative to what they otherwise would have been. And so one of the things that people had to do more was use that fork Daemon operator to say, well, I want this thing to continue beyond the life of its parent fiber. But that's also not ideal because typically maybe you want it to extend beyond the life of your parent, but you may not want it to extend forever. You still want it to be limited to some scope. So that kind of brings us forward to where we are today, where we're in the process of working on a concept of more explicit scopes. And so the idea is that each fiber would have a scope associated with it. And by default, when that fiber ended, its scope would end and it would execute any finalizers it had, so typically interrupting its children. But we would have a operator, let's call it ZIO.scoped, that would let us extend a scope to widen that out, to keep fibers alive for longer. And so this lets us, we think, achieve a little bit of the best of both worlds, where when you use scoped, you're saying, I want a fiber to continue beyond the life of its parent, but here's the scope that it makes sense for it to operate in. And you still have that fork Daemon if you really want to say this fiber should go forever, but we think most of the time fibers should have some type of explicit scope. So if you think about, like in Python, there's a library from Industry Trio. They have a concept of nurseries that you think about this as similar to that in some ways. So this is something we're working on. Don't have code out to show you yet, but a little bit of a preview of what's coming in the world of ZIO.
So now let's see how to write safer concurrent code. But because we introduced fibers and fiber supervision, now you earn the membership of Fiber Club. But hold on. First of all, you need to know about the first rule. Adam, tell them.
So I try to be cooler than I actually am and include at least one meme in each of my presentations that at least I think is funny. So this one's from Fight Club, and now we're not in Fight Club, luckily, but you've listened to more than 30 minutes of us talking about the details of fibers, so you're definitely part of the Fiber Club. But the first rule of Fiber Club is don't use fibers directly unless you have to. Fibers are fantastic. They're the building blocks of us delivering safe, high-performance concurrent solutions, but they're low level. So most of the time, there are going to be other combinators that are built on top of fibers that are going to do what you need to do and are going to have everything taken care of you, are going to be optimized for you. Someone's going to have thought about any corner cases. So go there first. That'll be your answer 90% of the time. And then the 10% of the time that you do need to do something customized, hopefully with what we've talked about today, your knowledge of fibers and what we've done with fiber supervision, you have the tools to do that, and it's easier for you to get that right.
Yeah, and there are common concurrency combinators built on ZIO. You can use the ZIO data type, and you can for example, run parallel computations, and the internal implementation in ZIO will take care of the fibers there and make sure that the fibers are not leaking resources, etc. And also about there are other data types built on ZIO that helps also to, for example, to have a mutable state in concurrent programs like the STM data type, and there is promise, etc. But now let's see some of these combinators by example. For example, if you want to get the first successful and faster computation, you can call race, and this will return the first, the fastest computation. And in case if there is one successful computation, the loser will be interrupted and its resource will be safely closed and released. And in case if you have many tasks and you want to take the fastest one, you can call race all. And this, like for example, here we want to take the first available service. Otherwise, we would just load the local service and we give like a chance of 2 seconds delay because we prefer to get from the other services. And in case if you have a computation, like parallel computations, you want to get the user and the profile at the same, and in a single operation, you can call ZPAR. This will internally interact with fibers and will give you, if both of them will finish, it gives you the result. And in case if one of them will fail, the task will fail. And you can also have, you can make a computation you can have a function that takes a list of IDs and compute. For example, here we fetch many users and we get the result in a single operation. So this is helpful to do in a single operation. And in case if you have resources, you can use brackets. And when you will fork this effect, it will, whatever will happen, for example, if there is an error or the effect will be interrupted or the operation will be successfully completed, this release action, which is the client.stop, will be executed. We will have the guarantee to execute the release action using bracket. And also if in case if because in bracket we need to define what we want to use, how we want to use this resource directly. And in case if you want to build your resource as a data type, you can use manager. You specify the acquired operation and the release action, and later you can use this resources and you in different fibers, and whatever will happen, your resources will be safely released. And as we mentioned in the first earlier, we can also use the ensuring, and this will it's not a very, like, actually I wouldn't prefer to use it for specific resources, because ensuring will take a new effect. It will not use the current effect. So this, in case if you have an extra action you would like to do when the computation will finish or will fail or will be interrupted. And sometimes you run to a situation that you want to decide and to have control over your fiber and your its execution context, and you want to switch the execution context in case if, for example, you have a database operations and this database already has an execution context. You can do your operations and you can call .on. This is this function is in ZIO, and you specify the execution context. And in case if you want to run your effect in blocking thread, you can call blocking. This is an internal it uses an internal execution context in ZIO, and it exists in ZIO internal blocking package, I think, or ZIO.blocking package, and this will run your effect in this blocking thread. So these are some of the operations, and there are more of them, but this gives you more guarantees that about your resource, about especially about how, for example, when you use a parallel in ZIO, it internally uses fibers and it will interrupt. In race, when you race two operations, it internally interrupt the loser action, and it will give you the successful one. So you will not worry if if there is an effect is running in background while you are not needing them. So all of this power is provided by ZIO functions.
So to summarize, fibers are the building blocks for writing concurrent and asynchronous code in ZIO, as well as really in other functional effect systems in Scala, as well as in many other programming languages. And fiber supervision is something that when we do need to use fibers, helps us do the right thing by default instead of needing to do more legwork and use more combinators to make sure we get what's the right behavior most of the time. But we've got a variety of combinators, a lot of the ones that Wiem just talked about, as well as data types like refs and promises and STM data structures, where you pick your exact number, but I'll call it 90% or more of the time, there are existing tools that have been built for you to take care of whatever you're trying to do. So reach for those first, but hopefully after this presentation, you have a better understanding of if you do need to write something that's more customized, how to use fibers to do that, and how some of the things that we've been doing in ZIO around fiber supervision are trying to have your back for doing that and make it easier and safer for you to work with fibers when you do work with fibers directly.
Yeah, and if you are you didn't check out yet ZIO, you can today you can check out the repository, and you will find also documentation. And in case if you have any question, you can join Discord ZIO group. Yeah,
and really just want to thank all of you for taking time out of your day to attend this presentation today. All the organizers of this conference for letting us get together virtually with everything that's going on in the world. All of the users and contributors to ZIO, I think we're up to 270 contributors now. So if you've ever been interested in contributing to an open source project, whether you have or not, or you're a functional programmer or not, it's a great opportunity. I think it's a really friendly community. So we'd really encourage you to check it out on GitHub, on the Discord. Also want to thank all the users who've been with us through the various release candidates and things that we've figured out along the way. I think we're definitely moving onward and upward, but we've been figuring things out along the way. So appreciate all of your patience. And finally, would like to personally thank John for being a mentor to me, as well as I think so many others in the community, and really creating this ecosystem. As well as Wiem for doing this presentation with me and being so great to collaborate with.
Thank you too, and thanks all of you for joining this talk.
Thank you for your presentation. I enjoyed it very much. We have a few questions. The first one is, can JVM just kill a thread? How would ZIO runtime know that it happened?
So generally, we want to try to avoid killing threads ourselves. There is just kind of a raw thread.interrupt method that you can call, but it's generally somewhat unsafe to do it because you don't have that guarantee around finalizers. So really, the whole interruption model is based around this idea of when you're interrupting a ZIO effect, you actually don't interrupt a thread. That thread just goes on to do something else and stops doing work on this set of computations. Just about the only time we will interrupt a thread is we have one effect blocking interrupt combinator that if you need to import a blocking effect into ZIO and there's no other way to interrupt it, we give you a constructor where you can say this specific effect, I want you to run on the blocking thread pool, and if I interrupt it, I want you to try to interrupt that thread, but that's generally something that you'd only use for pretty particular situations.
Okay, next question. What about Project Loom? Could it help ZIO Fibers, and how?
Yeah, so that's something that we've definitely been thinking about. We think that when that's available, there's definitely going to be a ZIO version that can take advantage of it. And in a way, a lot of the ideas we've been thinking about, part of the idea for this talk was bringing structured concurrency to the JVM. And that's really one of the ideas of Project Loom. So when we think about some of these principles for fiber supervision and how that should work, we very much have been consulting and thinking about what they're doing with Loom.
Okay, thanks. Another question. Earlier philosophy was to garbage collect fibers because they don't give us value. We would like to use. Why is it too early?
Yes, so it is important to garbage collect fibers because otherwise we can have a resource leak in some cases where if you're creating fibers and you're not explicitly interrupting them or joining them back, some of those fibers, if you don't do anything, can kind of hang around and ultimately create a memory leak. And so one of the changes we made is allowing garbage collection of fibers, but it's done in a way where a fiber will only be garbage collected if there's nothing else that's referencing that fiber. So in almost any case, it should not affect the meaning of your program. I think the only case that we've really run into it is in internal tests where you create very specific situations, and then we've got a combinator you can use to make sure a fiber doesn't get garbage collected.
Okay, there is one more short one. What is a ZIO instruction?
Wiem, you want to take that?
Yeah, I think a ZIO instruction, it's like for example, you have your program that print out in the console and then read from the console, etc. These are instructions.
Yeah, so ZIO is actually a data type that has a bunch of specific subtypes. So like flat map would be a subtype of ZIO, map, changing interruption status. And so what the runtime ultimately does is run through each of those instructions and execute them one by one and do what those instructions say. So if you're interested in that, definitely go on the GitHub. There's a file called Fiber Context that has all sorts of the details there. And we can also pick it up in the chat or after this.
Yeah, when we build, for example, an effect, a total effect, it is like when you call ZIO.effect total or something, it is itself an instruction, right? And then .flat map, it will transform to it. And then the next, yeah.
Okay, thanks again for your presentation.